What I'm going to talk about today is black holes, singularities, and the two-body problem. Now, why singularities? Because for some reason, for 50-some years, people have been trying to show that there are singularities inside black holes. In that same 50-odd years, there's never actually been a proof. So there's got to be a reason for this. And what I'm going to say is the reason is there are no singularities, except possibly in Schwarzschild when everything is spherically symmetric. Now, the first thing I better do is give a bit of a picture of the Kerr solution. This has got the inner and outer horizons.
No, excuse me, we don't see your slides. Are you sharing the screen?
Sorry, I changed the slide then. Did it work?
We don't see your slides. If you have problem with sharing, why don't you send us the slides? Then we will show for you.
Oh, if you don't see, you're not seeing the slides.
No.
This I've got my. Can you see? You can't see this. Jesus Christ.
No, just send us the slides. We will show it for you, please.
Yes, you can send your slides to me.
Okay.
I'm the chairperson of this session.
Okay.
I'll send you your email half an hour ago.
Okay, I'll try and do that. Why aren't they showing? I'm doing my best. Okay, I'll just. What for Christ's sake. I'm doing, I'll have it there in a moment. Here we go. Reply. Paste. Here they come. Okay, I just sent them to Yefei.
Okay. Yeah, I received your slides.
Sorry, have you got them?
Yes.
I sent them. Good.
Okay.
Okay. if you get slide 1 up, and then go straight to slide 2.
Can you see my screen?
Ah, great. Yes, it's on the screen. Thanks.
Yes. So when you
Yeah.
are you going when you change the slides, please say next.
Please,
You see, when you want to change the slide, say next.
next. Okay,
Okay, let's start it.
try next.
No, 这是我写的，是的呀。
It was a PDF I sent you.
Yeah.
Ah, great. There, that's good. All right, now, here's the standard picture of the Kerr black hole with the inner and outer horizon. The area or the region in between those two, I like to call the event shell, because it's more like a shell than a surface. Now, inside Kerr, there is this singularity. You've got to remember there is no physical meaning to this singularity, this circular ring. Just like in Newton's theory, where the force due to a spherical body is m/r², that doesn't mean that at r = 0, the force is infinite. It just means there's matter there. So we can forget everything inside that inner region, because inside that inner region, there's going to be matter of some form or other, which I'll talk about later. Next slide, please. Okay. The problem with the question of singularities for the last 50-odd years is that nobody has actually proved that a singularity exists inside a black hole. What they've generally proved is that either a singularity exists or there's some light ray whose affine parameter is finite in length. Now, it has been claimed that this is a terrible thing, and that if there's a light ray of affine length somewhere, there's a singularity. What I'm going to show is that in the Kerr solution, there are light rays whose affine parameter is finite. They are not of infinite length. All this means is that the affine parameter is not a very good indicator of whether a curve is infinite or not. Next slide, please. Okay, there are 3 usual coordinate systems for the Kerr solution. The one that most people use is the Boyer-Lindquist form. Why I mention Achilles Papapetrou there is he is actually the person who showed that if you've got an actually symmetric, stationary, that's independent of time's solution of the Einstein equations, empty, then it can be put in this form of this Boyer-Lindquist type form whenever there's no singularity along the axis at infinity. And that's true of Kerr. So, and furthermore, in a beautiful paper, which I had a preprint of about the time I found my solution, in this paper, he showed that the transformation from the form that one has it in to start with to this Boyer-Lindquist form is quite trivial and just involves a bit of algebra rather than solving differential equations. Anyway, that's why Achilles Papapetrou's name is on here. It's time he got credit for this. Now, from the Boyer-Lindquist form, you can, using what Achilles Papapetrou showed, you can get to the Kerr-Schild forms by this simple transformation. I haven't integrated these two. What this means is that the new t is the integral of the old t plus this function of r. Now, this function of r is singular here, where delta equals 0. So if we go back to the Boyer-Lindquist form, delta is r squared minus 2mr plus a squared. So when delta equals 0, this metric is singular. There's a rho squared over delta. Basically, the coordinate system breaks down. Now, the roots of delta equals 0 are the two event horizons. That's one thing that is easy to pick out from the Boyer-Lindquist form, is where the event horizons are. They're where this delta is 0. Anyway, what this means is that when you integrate this, because of the singularity, the change in the time is actually infinite, either plus infinity or minus infinity, when delta is 0, i.e. at the event horizons. Now we can do this transformation, and I can't see all my slides, by the way. I can, there, I'm seeing a wee bit more now. There's another thing we can pick out of Boyer-Lindquist. If you notice, if you change the sign of t and phi, both, or dt and d phi, that's the only place the t and phi occur, then since this is squared, there's no change in the metric. There's no change in the metric here, and t and phi don't appear elsewhere. So the metric is invariant under this flipping of the time and phi. What this does is, if we knew where the principal null direction of that the Kerr-Schild metric was built on, if we knew where the ingoing one was in here, we could find the outgoing one just by a simple change in phi and t. So what this means in the end for us is that this transformation, I can either go one way to the original Kerr-Schild form with an ingoing set of null rays going in through the event horizons, or I can go the other way to the outgoing null rays. So next, please. So that means that when I do that, there's just a few changes of sign in the metric. If I go from this rather nasty looking differential form here, which is actually flat space, that part, the first part before the 2mr over rho squared is flat space, that can be transformed to the form of dt squared dx squared plus dy squared plus dz squared. The other term, the squared term, is the square of what happens to be a light vector. Now, for those who don't know, The beauty of this form of the metric is that the determinant of it is independent of the mass, because this is a null vector, not only in the full metric, it happens to be a null vector in the background flat space. So that allows us to raise and lower indices very trivially here. If this is the covariant form of K, this is the contravariant form, and these are true in the background flat space or in the full metric. Okay, notice they're very similar. The only difference between the ingoing and the outgoing form of the null vectors is the change in sign. One is going in, one is going out, and A appears to change sign. Well, that's okay, because as you go, when you go from Boyer-Lindquist to Kerr, you have to do a spin of the whole coordinate system in order to straighten out the ingoing rays. Now, if you want to look at the outgoing rays, you have to do the opposite spin. So that's why there's a change in sign. Next, please. Okay, now, this is those are effectively the two sets of principal null vectors. Now, one of them is obviously obvious in the form that I originally gave the metric, because that's the principal null vector that was displayed in the coordinate system. What about the other? This isn't so obvious, except down the axis, because down the axis, since it's rotationally symmetric, neither principal null vector can have a component off the axis. So they both point down the axis at that point. Now that means that if I look at down the axis with d phi and d theta are 0, okay, just at the dt and dr part, then ds squared equals 0 gives me the two null vectors on the axis. This is just a trick that can be used there. So if I look at the roots of this has got a root dt plus dr also. So dr over dt equals -1 is the incoming geodesic. dr over dt equals this, so the r squared minus 2r plus a squared over the factor which has no zeros is the other one. This is negative between the two horizons. It's positive elsewhere. What that means is on the outside, this vector can struggle its way out to infinity, traveling very slowly at the start, speeding up as it gets further out. Inside the horizon, both horizons, in the part that appears to have a singularity, again, this light ray can travel towards the inner horizon. It can travel, so you can have light rays going up and down the axis inside the inner horizon. Now, that actually says one thing. There's no trapped surface inside the inner horizon. So any talk about trapped surfaces and what they may imply doesn't tell us anything about what's going on inside this inner horizon. Okay, now that says, next please, that you can see that if you plot r dot against r for this outgoing null geodesic on the axis, if you notice it's positive here, positive in the left-hand segment, negative, then positive. Okay, what this means is that this on the inner, But on the event shell between the two horizons, this is doing its best to go out, but it can't. It's falling slowly in. It's asymptotic at both ends to the event horizons.
Open.
It's asymptotic at both ends there. Yes. The can I have the next slide, please? Okay. Ray-Shaduri's equation is what was being used by many people to prove there are singularities in various places. Ray-Shaduri's equation says that eventually, if you've got congruences with certain properties, the light rays will meet again at a singularity. The only trouble is,
Talk longer. Okay, we'll see.
I still online? The only trouble with this is Ray-Shaduri's equation fails if the null rays that it's talking about have not got infinite affine length. And since, as I said before, affine length is a very poor estimate of where a light ray is going, this theorem doesn't work in Kerr or anywhere else where one is trying to prove a singularity. There is actually no singularity theorem, either Roger Penrose's or Stephen Hawking's, which works to prove anything of interest, because they all require infinite affine length for light rays. And this breaks down in all the situations where we might get singularities. Next, please. Okay, now let's go back to the Kerr solution. Let's suppose you've got a neutron star, a rapidly spinning neutron star. The metric outside the neutron star is probably fairly well represented by the outside of the Kerr solution. Now, please don't mention singularities, because the neutron star has got its own internal structure. I don't know what that is, but it doesn't matter. Nobody is saying that a neutron star has got a singularity inside. Nobody's saying that the Earth has got a singularity inside just because Newton's theory would give a singularity if there wasn't matter present. Okay, the neutron star has got matter present, no singularity. Suppose we dribble neutrons or other whatever onto this and gradually increase its mass while keeping it spinning fast. What's going to happen? It's eventually going to reach a stage where there is not enough angular momentum inside this body to counteract the attractive forces, the Newtonian type attractive forces. So it is likely to collapse to a black hole, but it doesn't have to collapse very far before the angular momentum forces can counteract the gravitational forces, the other forces. So what I'm saying is, if this is a fast-moving neutron star, can we go back a slide or two, please? Well, it doesn't matter. What I'm saying is that inside the inner horizon, you have got a rapidly rotating neutron star, which, because the outside of it cannot be a light-like surface, it's got to be a space-like surface. Its outer boundary will not be at the event horizon, it will be inside. And it's as likely to be some R equals constant surface as anything else. Now, when does where does the singularity come in? I don't know, nor does anybody else. There's been 50 some years since I found my solution. And up to that time, there has been no theorem which says there's a singularity inside. Now, if you look more carefully at Roger's theorem and actually read it, what Roger says is either there's a singularity inside or there's a light ray of finite affine length. These light rays that Roger was talking about for the Kerr solution are basically a set of the second principal null directions, the slowly collapsing ones. If I take a trapped surface just inside the event horizon, the outer event horizon of Kerr, and I look at the principal null directions, these ones that are leaving that surface, but traveling very slowly. They're trying to point outwards, but they can't because everything points inwards on this trapped surface. If I look at those and I plot them in the only metric for Kerr that we've got that isn't either singular somewhere, have coordinate singularities at the event horizon, or talking about stuff that is supposed to have occurred back an infinite time before the Big Bang, which is a problem with the second Kerr-Schild coordinate system I put down. If we talk about outward falling Kerr, sorry, the inward going Kerr, then this set of null rays, the ones that Roger's talking about, all are asymptotic initially to the outward event horizon, but of course that's back before the Big Bang. Here we're talking about the actual formation of the black hole, just like with Schwarzschild. So you can forget it there. These null rays are falling in towards the inner horizon. They are asymptotic to it. They never reach it. Now, there are going to be people, and I've had them say this to me, that what about the maximal extension? You can extend this Kerr solution to a beautiful picture with 99 different blocks. Okay, the maximal extension. Well, the problem with all this is if let's suppose I stand on the North Pole or stand above the North Pole of this Kerr solution, and I start throwing rocks in. Now, I'll throw a rock in every time a new day appears for me. Okay, one rock a day. They will fall in a finite time, passing through both the horizon, the event shell, through the inner horizon, and will end up on the rotating neutron star inside. That, okay, because let's say I keep doing this, they will keep falling through and they will hit the event horizon at finite times in the Kerr-Schild formulation. Furthermore, because of the fact that this whole metric is independent of time, they will do it in a constant, they will do it, the time between their arrival on the inside will be a constant. So I can follow that. If I was living on the neutron star inside, I could watch these rocks falling time after time after time after time forever. And I'll tell you what, none of these rocks would fall into some magical other branch of Kerr in some other universe. So, and they would all cross these infalling light rays that don't make it through the inner horizon. Inside the horizon, the inner one, between the apparent, this inner horizon and the surface of the neutron star, there's a region which is highly unstable, of course. There's no question about that. And there are going to be a number of talks given about this. But if I were alive on the surface of this neutron star, I'd have to be about a millionth of a millimeter in size to withstand the forces. But I could throw rocks upwards off the surface, which would approach the inner horizon and then fall back. I could even send light rays up towards the inner horizon. These light rays would fall back mostly, except for the ones which are actually the principal null direction. So things can happen in there, but they're very nasty. Next slide, please. I'm going to run out of time soon. I was going to talk about Einstein-Infeld-Hoffmann equations. Now, this 1938 paper by Einstein, Infeld, and Hoffmann was one of the most important papers in relativity. What they showed was that you could actually start to solve the two-body problem using these methods as long as things were slow moving. Now, there was a problem with their papers, and that was that what they showed in the first paper was that if you tried to solve the linear equations for the assuming very slow motion, then there were certain integrals which were zero. This integral here that I wrote down from their paper was comes from basically Stokes's theorem, used cleverly on the Einstein equations, these equations. Now, the trouble with this was they found that in order to solve the first order equations, they had to have the mass moving with zero acceleration. Then in the next order, they found that the Newtonian forces had to be zero. Well, obviously there was something wrong. They wanted the acceleration to equal the Newtonian forces. So they spent the next 20 years, or at least Infeld did. Einstein got out of it after a couple of years. They spent this 20 years trying to prove that they could do this. And finally, when I got started as a graduate student, Infeld had shown that one way to get around it was introducing dipole moments in every approximation order. Things had become a real mess. Now, I looked at these equations, and what I realized was that, first of all, there were more integrals that they had missed, which came from angular momentum, the conservation of angular momentum. They hadn't written down these, so they were never going to prove that they could solve their equations unless they satisfied the angular momentum equation. Next equation, please. Next slide, I mean. Okay, so what it came down to, you can read this for yourselves, was that you can't solve, you literally cannot solve the set of linear equations, phi mu nu equals lambda mu nu, in each order exactly. They cannot be solved. What you have to do is simultaneously solve for the mass equations and the accelerations and the spin equations. You can then get an approximate solution of these equations in each order if you do that. Okay, next slide, please. So the problem is you can't satisfy the coordinate conditions exactly simultaneously. One thing I did show back in 58 when I sorted this stuff out was that you could change the conditions from step to step, choosing whatever was convenient from the first order, second order, third order, etc. And in particular, what should have been done is that we should have started with the outgoing Kerr-Schildt black hole solutions, because these are exact linear, they're exact solutions of the linear equations. They give you a far better start than what was actually used, which was, something like the original Schwarzschild solution. Okay, so what I'm saying here, which slide am I up to? Is this the second last? What I'm saying here is that if the Kerr-Schildt form had been used as the first approximation in these approximation methods, it would have been, first of all, a hell of a lot better. See, the point is, if you start with the Kerr-Schildt form, all you ever get from then on out are corrections which involve not the m squared, but m prime squared. You never get any more self terms. They're always just cross terms. Well, next slide, please. Is there another one, or was that the last one? Okay. I think there's another slide in which I want to just say something about. Can we next, please? Or if not next, the previous. Okay, it was the previous, yes. Jose and Jorge et al. Showed that if you use a test body motion near a black hole, test body motion, that's what they used. They got results which were very close to those by numerical relativity with a tremendous amount of effort, and the efforts of the people who are using fast approximations and slow approximations. They actually got results which were practically identical. Now, why was this? I was there when they came up, when Jose produced his results, which only took a week or two, by the way. And I said at that time, it's because of the Kerr-Schildt form of the metric. So what I believe is that you can forget about all those massive calculations, use a Kerr-Schildt approximation, which is like what Jose used, except he started with the Boyer-Lindquist form, which is not so appropriate for this. So using that should give the templates for LIGO a hell of a lot easier and faster. So I better stop there because I've used up my time with screwing around with this, these slides and things. Finally, what I can say is forget the singularities. Anybody who thinks that there are singularities should provide a proof, or a proof that there are singularities inside black holes. Remember, Roger did not. he said either a singularity or something else. What I'm saying is it's the something else. And there is, in 50 odd years, no other proof. Thank you. I'll stop there.
Thanks. Thanks, Professor. So because we start this talk 8 minutes later, so we still have 2 minutes to take questions.
Okay, good.
So you can raise your hand.
There is a question in Q&A.
Mathematics is a funny thing. You know, it gives clear-cut answers. Here we have what is more like a religion, in that people have been told for so long that there are singularities in black holes that they believe it, and nothing that people can say is going to stop their belief, because they know that somewhere there's a proof of that, only that hasn't been found, but somewhere there's a proof. I feel I should give a prize, say $1,000, to anybody who can actually prove there's a singularity inside black holes. Thank you. No more questions. There never were any questions.
Excuse me? Hello?
Hello, are we still there?
Yes. So my name
Now we can hear the next talk.
Yeah, so my name is Julius Serbenta, and I don't know whether this was your response to this question I wrote in the Q&A related to exactly solving the geodesic deviation equation for Kerr black holes, because it can be
the interior.
Okay, well, for interior, either case, because we have Killing vectors and tensors, and this allows us to integrate these equations at least once. So I wonder whether the solution would bring a more compelling argument to this question.
Obviously, there are lots of solutions of the interior, and that's the whole point. I didn't mention it, but it is quite possible if you have, let's suppose you've got two almost Schwarzschild particles, very slowly spinning bodies of equal mass, equal small spin, collapsing together. Now, what are you going to get inside when an event horizon eventually forms? Okay, I am almost certain that what you're going to get inside is a region with two orbiting small spinning particles. They're not going to join together. They're going to stay spinning. However, they can't lose the orbital angular momentum, can't be sent to the outside because nothing can get out. So the orbital and angular momentum is not going to decrease. And so there's no reason why they shouldn't keep spinning forever. But that's sort of irrelevant. The point is that the outer horizon will form, the inner horizon will form, inside will be a big cavity with two small black holes orbiting each other. No singularity apart from the two slowly spinning black holes. So when you talk about finding an interior solution, there's an infinity of interior solutions possible. And that's where this whole business of the stability or lack of the inner horizon is so important. One believes that the black holes on the outside degenerate down to having only the two parameters, mass and angular momentum. What happens on the inside, though, is completely different. you could have a lot of quadrupole moment or anything else on the inside. And it's not going to radiate away.
Okay, thank you.
Okay. Due to we run out of time.
Okay. Okay. Well, onwards and upwards. Next talk.
Yeah.
I'm ready.
Yeah. Are
Yeah,
you ready? Can you?
Yeah, I'm ready. I'm going to share screen.
Yeah.
I'm looking for the PowerPoint right here. Share.
No.
Just a sec. Do you see it?
Yes, it works.
Can you see the? Okay. Yeah. I'm ready. If there's a connection problem, maybe give me 2 minutes to fix it. Okay. Okay, I'm ready to begin. If everybody else is ready.
Yes, but we cannot see the full screen.
Okay, just a minute. Can you see it now?
Yes.
Full screen. I can begin, right? I can begin now. Okay, so yeah. So this is the title of my talk: the irreducible mass of Christodoulou, Ruffini, Hawking mass formula. Now, this talk is to celebrate the 50th anniversary of the discovery of the mass energy formula of a Kerr-Newman black hole in 1971 by introducing 3 new theorems in black hole physics. So first, congratulations to Dimitris Christodoulou and Remo Ruffini for their remarkable discovery of the irreducible mass of the black hole, one of the most important concepts in black hole physics. Now this year is also the 50th anniversary of the renormalization of Young-Mills theory in 1971. So congratulations to Gerard de 't Hooft and the late Martinus Veltman for their elucidation of the quantum structure of weak interactions, which is one of the great achievements of 20th century physics. Now here's the irreducible mass formula. On the left, we have the total mass m. On the right, we have the irreducible mass. Q is the electric charge and J is the angular momentum. Now, 50 years later, the irreducible mass has gained new significance besides energy extraction. It can also determine black hole dynamics and structure. To begin, we'd like to explain the definition of the black hole. The mathematical black hole has a singularity hidden by a horizon. However, neither singularity nor horizon has been observed. And compact objects like the one at the center of our galaxy are also called black holes in common usage, even though their nature is still unknown. This difference is emphasized by the 2020 Nobel Prize to Roger Penrose. The citation is for the discovery that black hole formation is a robust prediction of the general theory of relativity. And to Reinhard Genzel and André Ghez, the citation is for the discovery of a supermassive compact object at the center of our galaxy. The term black hole is not mentioned. Now, between 1965 and 1985, several important theorems on classical black holes were discovered. They are known as the singularity theorem, area non-decrease theorem, uniqueness theorem, and positive energy theorem. Now, in recent years, 3 new theorems are found, which were previously unexplored in the Hawking era. They were discovered, developed by me based on quasi-local energy and angular momentum consideration. Remarkably, they all contain the irreducible mass. They are called the horizon mass theorem, external energy theorem, and moment of inertia theorem. Now, in part 1, we discussed the horizon mass theorem. The theorem can be stated like this. For all black holes, neutral, charged, or rotating, the horizon mass is always twice the irreducible mass observed at infinity. The horizon mass theorem is the final outcome of the quasi-local mass applied to black holes. Now, the meaning of quasi-local mass is this. The quasi-local energy is given in terms of the total mean curvature of a surface bounding a volume for a gravitational system in 4-dimensional space-time. The Brown and York expression from 1993 is shown here. It involves an integration over the surface curvature. Here, K is the curvature of the surface, and K0 is the curvature of a background surface, usually taken to be 0, and sigma is the metric on the surface. Now, applying this formula to the Schwarzschild black hole, we find the total energy contained in a sphere enclosing the black hole at the coordinate distance r is given by this formula here. Now here you notice a square root factor, which is the curvature in the Schwarzschild metric. Now at the horizon, the square root factor will vanish, and the result for the energy is very simple, and it simply gives twice the asymptotic mass of the Schwarzschild black hole. Now, so this is the first case of the horizon mass theorem. For a charged black hole, the total energy contained within a radius at coordinate r is shown by a similar formula. Again, you notice a square root factor, which is the curvature of the charged black hole space-time. Again, at the horizon of this charged black hole, the square root factor will disappear, and we have a simpler result. Now, the irreducible mass is the final mass of the black hole when its charge is neutralized by adding oppositely charged particles, extracting energy from the black hole. So the irreducible mass is shown by the bottom formula here. It involves the charge Q and the total mass M. Now, the horizon mass in this case is the mass contained within the horizon as seen by an observer at the horizon. It's given by this expression. And remarkably, when you compare this with the irreducible mass, it is simply twice the irreducible mass. And this means the horizon mass depends only on the energy of the black hole when it is neutral. So here we have the second case of the horizon mass theorem. Now, next we go to a slowly rotating black hole. The total energy now has only an approximate expression because the problem is very complicated. At the horizon, it is found that there's very little rotational energy. And this means the horizon mass is almost twice the irreducible mass, but not exactly. This work was done by Martinez in 1994. Now, for higher rotations, the calculation is extremely difficult and no useful expression can be found. So at this point, progress on quasi-local energy for rotation stopped because no analytic method or numerical evaluation could achieve an exact expression for the horizon mass. Now, a breakthrough occurred 10 years later when I explored this problem with the area concept. Now, it is known that the area of a Kerr black hole can be expressed in terms of the irreducible mass again. This was the work of Christodoulou and Ruffini. On the other hand, the area of the Schwarzschild black hole is given in terms of its asymptotic mass, as shown here. Now, the two can be related if we invoke Hawking's area non-decrease theorem. We see the area of a Kerr black hole is the same as the area of the final Schwarzschild black hole when rotational energy is extracted in a smooth and reversible process. And since the irreducible mass of the Kerr black hole is the Schwarzschild mass m, and since the horizon mass of the Schwarzschild black hole is proven to be 2m, therefore the horizon mass of the rotating black hole is twice the irreducible mass. Now, so this is an elegant proof. Now, we have therefore found all three cases for the horizon mass theorem. Now, so far the result is mathematical, but is this important to physics? Well, we have two processes to show that the horizon mass is absolutely important. First is the black hole collision using the example of first gravitational waves observed in 2015. Two black holes merged to form a final black hole, releasing gravitational wave energy. According to LIGO, the two black holes have masses of 36 solar mass units and 29 solar mass units. They form a final black hole of 62 solar mass units with 3 units left as gravitational wave energy. Now, if you look at this, this is energy conservation at infinity. Now, if you look at this process in detail, you find that there's something missing because the waves were produced very near the horizons of the two black holes. And they require a huge amount of energy to reach infinity. So where's the missing energy come from? So we can explain this with the horizon mass. By calculating the horizon mass for the two black holes, we found that one has a mass of 71 solar mass units. The second one has 57 solar mass units. The final black hole has a mass of 116 solar mass units. 3 units are for the observed gravitational waves. 3 units are the redshift energy, and the remaining 6 units are for other factors. Since we use round-off numbers here, and there were uncertainties in the determination of these masses by LIGO, and there's a further cosmological redshift, which requires energy. Now, the second process is none other than Hawking radiation. Black hole radiation is only possible if the horizon mass is greater than the asymptotic mass, because it takes an enormous amount of energy for a particle released near the horizon to reach infinity. And this energy comes from the black hole. Now, in part 2, we discuss black hole rotation. The external energy theorem can be stated here. the rotational energy and electrostatic energy of a general black hole exists completely outside the horizon. This is a direct consequence of the irreducible mass. By definition, the irreducible mass does not contain electrostatic or rotational energy. A rotating black hole does not contain rotational energy inside the horizon. Therefore, rotational energy exists outside. And similarly, an electrically charged black hole does not contain electrostatic energy inside. Therefore, electrostatic energy exists outside, like a metal conductor. Now, if we consider quantum particles, we see that quantum particles carrying electric charges and spins cannot exist inside the black hole. They can only stay outside or at the surface. Since all matter particles in nature are quantum particles, this makes the interior of the black hole completely hollow. Now, according to Tomonaga, every charged particle has a spin, and he observed that nature was not satisfied with a simple point charge, but required a charge with spin. Now, we can make this theorem more general by introducing the external energy paradigm, which states this: all energies of a black hole are external quantities. They include constituent mass, gravitational energy, electrostatic energy, magnetic energy, rotational energy, heat energy, and so on. Now we finish the second part. We go to part 3. This is about the extended structure of black holes. The moment of inertia theorem is shown here. A black hole with an angular momentum and an angular velocity has a moment of inertia. It is given by coefficient times the Kerr mass times the ergosphere radius squared. When the rotation stops, there's an irreducible moment of inertia, which is given by the irreducible mass times Schwarzschild radius squared. Now, the expression I equal to mr squared is the rotational equivalent of the formula E equal to mc squared. Now, the Kerr metric was discovered in 1963, and it ushered in a new epoch in general relativity and astrophysics. It is absolutely indispensable for the study of rotating black holes, and I believe that it deserves a Nobel Prize. The Kerr solution is shown here in physical quantities. This way we can easily read off the metric coefficients and apply to a particular problem. And this is what I do for the moment of inertia of the black hole. A puzzling question which was never asked was this: do black holes have moment of inertia? The definition of moment of inertia is always angular momentum compared to the angular velocity of a rotating body. Both these quantities are well defined in the Kerr metric, so we expect a definite result for this ratio. Now, if there's no rotation, both these quantities are zero. So we wonder what can happen here. Is there a result for the Schwarzschild case or not? So we calculate the angular velocity of the Kerr black hole at the event horizon. We obtain this rather formidable formula here. On the left side, we have the angular velocity omega. On the right side, we have the angular momentum J. in 2 places and the total mass in 3 places. Altogether, there are 24 quantities here. In the end, they combine to give a single number, which is expressed in radians per second. Now, this is quite amazing. And this is an exact algebraic equation. Now, next, we rearrange the previous formula in a heroic way so that the angular momentum J is on the left and the angular velocity is on the right, and the remaining parts are the moment of inertia, is the moment of inertia of the curved black hole. The crucial step here is to be able to extract a radius factor, which is 2gm over c squared. Now here, the mass is the Kerr mass, including rotational energy. And this radius factor is actually the ergosphere radius from the Kerr metric. Now, so there's a numerator and a denominator. Now, the denominator involves the ergosphere radius, the angular velocity. They combine to give an ordinary velocity, and then divided by the speed of light, it becomes a number, dimensionless number. So the whole denominator just becomes a coefficient in this expression. And the numerator, we have the mass and the ergosphere radius. So the structure of the moment of inertia is a coefficient times a Kerr mass times the ergosphere radius squared. Now, when the rotation stops, we expect to have a Schwarzschild black hole. In this case, the angular momentum's angular velocity squared will become 0 first. The Kerr mass will become the Schwarzschild mass, and the ergosphere radius will become the Schwarzschild radius. So the moment of inertia of the Schwarzschild radius, Schwarzschild black hole, is irreducible mass times Schwarzschild radius squared. So the formula is very simple. I is equal to mr squared. So what we find here is that every black hole has a moment of inertia, including those that do not rotate. Now, since the Schwarzschild black hole does not have an axis of rotation, the center is the point of symmetry. And spherical symmetry requires all mass of a Schwarzschild black hole to be located at the Schwarzschild radius. So the black hole object is a hollow, massive shell, and singularity does not exist. So I have a physical reason for the non-existence of singularity. So the black hole is like a mechanical body. In conclusion, we see that these new theorems show that what is believed to be a black hole is a mechanical body with an extended structure. The mathematical black hole with a singularity was proved at a time when the moment of inertia was not known. This was 1965. And we believe that astrophysical black holes are likely to be horizonless, massive, compact objects from which light cannot escape. So this is the end of my presentation. And finally, I have a picture of Hawking and me in a conference in 1996. Thank you so much. Okay. Are there any questions? Professor Kerr? Okay, let me go back to.
Excuse me. I have a remark. The following.
Yes, yes,
Yes. Just to draw your attention to our talk.
yes.
Parallel session thermodynamics about the same problem.
Okay,
The main result that you can derive the mass formula for horizon mass in some field theories, not pure gravity, Einstein Maxwell, and some generalization using Tomimatsu approach, which
all right.
can be found in citation in our talk. Thank you.
Okay, thank you. And Professor Kerr, can you hear me?
Yeah. Okay. So you want to have the black hole Schwarzschild replaced with a shell at the horizon. It's got a slight problem because everything that is moving near there is moving inwards at the speed of light, isn't it? I don't know. This, if you can do that, you could put anything at the center. You won't have to fit any boundary conditions or anything. And I think you'd have trouble fitting the boundary conditions of the outside of Schwarzschild with a shell at r equals 2m.
That seems right. That seems to be right, but the equation which I showed, they are exact. So how would you explain the presence of the moment of inertia then, if there's nothing at the horizon?
If I take a bunch of classical ideas and mix them with a bunch of non-classical ideas and definitions from general relativity and definitions from classical physics, I'm likely to end up in a mess and prove just about anything I want to prove. I don't know. It just and this is not just a problem with what you were saying here, but it's a problem in physics in general, in that a whole lot of ideas have been carried over from 19th century physics and attempted to be pushed onto onto universal size objects with general relativity rather than Newtonian physics.
Yeah.
So that's going to be a problem. It's a problem for me to understand what you've done.
Maybe, but so far the singularity theorem was proved with classical particles. And
no, there was never a singularity theorem. Sorry.
Yes, right.
Roger Penrose did not claim to prove the existence of a singularity. He claimed that either there's a singularity or there's a light ray of finite affine length inside the black hole. Or, and here's another one that I could mention, or the weak energy condition wasn't satisfied. Now, all these energy conditions are holdovers from 19th century physics. I have no idea what the what a classical approximation to a quantum mechanical universe should be, but I don't know whether this weak energy condition is anything but a desperate attempt to figure out something that can be used to prove theorems. Just remember, if it hadn't been the weak energy condition, it would have been the strong energy condition or the left-sided energy condition or some other energy condition, whatever was needed to prove a theorem. So, for instance, with Schwarzschild, people say that you can't have a spherically symmetric body without a singularity, Schwarzschild. The trouble is that just because the angular momentum is at 0 doesn't mean the body's spherically symmetric. It can be anything but spherically symmetric. It can have quadrupole moments. It can be what's the word? When everything is a real mess and bubbling away, and lots of things can be happening, in which case taking an average like the weak energy condition may be fairly meaningless. It is for me.
Okay.
Okay.
We certainly like to understand more.
Yeah. I'm sorry.
Right.
What is it when bodies are anyway, spherical symmetry doesn't solve the whole problem for bodies that aren't rotating.
Okay.
Okay. I think we should end this talk.
Okay, thank you.
Yeah. First,
Thank you for your talk.
can you share your screen? Yeah. Our next speaker is Lorenzo Amati. He will talk about the cosmology and multi-messenger astrophysics with gamma bursts.
Yes, good morning or good afternoon. I will share my screen in a while.
Yeah.
Okay, you should see a presentation. So thank you. Thank you very much. Many thanks to Remo, Gregory, Robert, and all the organizers for giving me the opportunity to talk to you about gamma ray burst and specifically their relevance for cosmology and multi-messenger astrophysics, which is still to be fully exploited. So for those of you who are not so expert of gamma ray bursts, most of you are aware, but just a very quick recap. Gamma ray bursts are huge flashes of X-ray and soft gamma ray radiations coming randomly from the sky, from random direction at random time with random like curves, so count rate as a function of time. You know, at these energies we are counting photons, so these detectors basically are counters. So you count, there is a background like a seismograph, and then you have this, as you can see on the top left, these bursts. These were discovered in the second half of the 60s by military satellites. And then it was realized they were coming from space and not from the atmosphere, not from nuclear explosions, from nuclear bombs in the atmosphere. It took several decades before we could understand something of these outstanding phenomena. So the very impressive things here is that these are really outstanding phenomena occurring more or less once per day. At least they are detected once per day by low Earth orbiting satellites carrying on board these detectors. And for 30 years, we were not able to know the distance, and so the luminosity, the radiated energy. So there were conjectures about the origin, the progenitors, the emission mechanism. But for 30 years, we were stuck with only basic information like the one on the top right, so that there are two main classes of gamma ray bursts, short ones lasting from a few tens of milliseconds up to a few seconds, and long ones which can last from a few seconds up to typical minutes. And then their direction in the sky, the direction distribution is isotropic, so they're actually coming from random directions. And then, as you can see on the bottom right, at the end of the 90s, thanks to the DepoSAC satellite and the efforts by many telescopes on the ground for following the localization, the first accurate localization provided by the DepoSAC satellite, it was possible to detect the so-called afterglow emission, so the fading multivalence emission following the burst in the X-gamma rays. The afterglow can instead detected from the X-rays down to the optical near infrared and the radio. And through absorption spectroscopy or direct imaging of the host galaxies of these events, it was possible to establish at the end that the distance scale is cosmological, as you can see, and long gamma ray bursts have been detected up to a redshift of more than 9, which means a few 100 million years after the Big Bang. And the radiated energy is huge. In the assumption of isotropic emissions, they can radiate more than 10 to the 54 erg in a few tens of seconds, which means more than all the energies that will be radiated by a star like the sun in all 10 billion years. So it's really, we're talking about the most extreme electromagnetic phenomena in the universe. The many efforts, observational and theoretical efforts going on also in the last 20 years, we came up with a basic standard scenario, even if, of course, the group by Remo and collaborators is developing a much more sophisticated scenario. This is the basic idea in the community, supported by several observations, that long gamma ray bursts are actually producing the core collapse of very massive peculiar stars that die where they were born. So they actually are located in star-forming regions within star-forming galaxies, whereas short gamma ray bursts are produced by neutron star onto star black hole mergers, and as was found and conjectured since many years, at least a fraction of them may be produced by neutron star black hole merging. So the merging of neutron star black hole systems. So why so much interest? Of course, gamma ray bursts are a phenomena, as said, so extreme that involve many fields of fundamental physics and astrophysics by themselves. Here I focus on their capabilities for cosmology and in perspective multi-messenger astrophysics. So of course these long gamma ray bursts that I said are detected up to the very early universe, as is sketched here. They can be originated up to the few 100 million years after the Big Bang, when the first stars and first galaxies were forming. And so we have with long gamma ray burst a tool, a cosmic beacon, that can pinpoint the explosions of the first stars, can illuminate, if you wish, the first primordial galaxies and tell us not only their existence, the basic properties, but also the metallicity evolution, the neutral hydrogen evolution, and so tell us much about cosmic ionization, for instance. And also, furthermore, they could also be used, as there are many investigations using them as possible standardizable candles to be used for investigating the geometry and expansion rate of the universe. At the same time, as I mentioned, short gamma ray bursts, so the two main flavors of gamma ray bursts, long, much interest for cosmology, short, much interest for multi-messenger astrophysics, because as you know, of course, in 2017, there was this detection of the first gravitational wave from a neutron star merger by LIGO, and the simultaneous detection only 1.7 seconds after the gravitational wave signal of a short gamma ray burst detected by the Fermi gamma ray burst monitor in a direction, from a direction consistent with that of the gravitational wave. And as you can see on the right, on the bottom right, the detection of a near infrared counterpart, which was then found to be produced by the radioactive decay of the very heavy elements being formed after the merger, because in this very neutron-rich material, the radioactive decay of these elements producing near infrared emission and characteristic features. So let's start focusing on the use of long gamma ray bursts for cosmology, as already anticipated. Here, the idea is of exploiting the fact that they are so luminous and they emit most of their luminosity in the X and gamma rays that are poorly absorbed by the interstellar intergalactic medium. So they can be detected and are actually detected up to the very redshift. Again, you can see here on the right another sketch putting gamma ray burst in the cosmological context. And as you can see, they can be detected up to the so-called cosmic dawn, when we're talking about a few 100 million years or even a few tens million years after the Big Bang. So just at the end of the so-called dark ages, when all the neutral hydrogen was neutral, stars and galaxies still had to be formed. So instead, at this epoch, the first galaxy and stars start illuminating the neutral hydrogen, and the universe start to reionize the neutral hydrogen, starting the so-called cosmic ionization process. And as again, if I go to the next slide, of course, so you can see more in practice how impressive are the capabilities of long gamma ray bursts for these purposes. What you see on the bottom left is actually the direct image of a star exploding a few 100 million years after the Big Bang. So actually, there are nowadays a few very bright, very massive galaxies that have been detected by the Hubble Space Telescope frontier field, for instance, at this very, very high redshift. But these are only very bright galaxies, the tip of the iceberg of the bulk of the population of the primordial galaxies, and mostly through lensing. Instead, here, with gamma ray burst, while catching the fading afterglow, as I mentioned, the electromagnetic, in this case, near infrared emission following the burst, we directly detect an object and the residual of the explosion of an object these very early epochs. So, for instance, if we simply could get a statistical sample of many tens of very redshift gamma ray burst, we could contribute substantially to the understanding of the evolution of the star formation rate up to the primordial universe. As you can see on the bottom right, this is the star formation rate evolution as inferred through many methods, and at redshift higher than 5 or 6, so the first billion years of the universe, where the understanding of the star formation rate evolution is fundamental, not only by itself to understand the formation and the population of first galaxies, but also because the first stars, the ultraviolet photons emitted from the first stars, are thought to be the main origin of the cosmic ionization. But this is still very much debated. So it is, of course, fundamental to know how the star formation rate evolves in the early universe. And as you can see, there is a lot of uncertainty if you consider the green points or even the shaded regions that are extrapolations from the very massive galaxies. There is a lot of uncertainty. Instead, if you consider the red points, this is what could be obtained with a sample of a few tens of gamma ray bursts at redshift than 6. So a huge improvement in the accuracy of the determination of star formation rate evolution. This is because, again, now this star formation rate evolution at redshift than 6, so first billion years of the universe, is inferred from the few very bright galaxies that are detected, and you have to make assumptions on the luminosity function of these very, very primordial galaxies that you actually don't know. Instead, with gamma ray burst, you can detect directly the exploding stars, but not only. If you have a look here at these 6 images, so on the top left, you see the fading after, as I mentioned, the residual of the explosion that is fading and disappears. So if you point a very sensitive telescope to the direction of the gamma ray burst, of this very redshift gamma ray burst, after this light is faded away, the afterglow fades away, you see nothing. These are images taken by the Hubble Space Telescope, so one of the most sensitive optical facilities. You can see nothing. So we know that in these directions, at this redshift, there are 6 redshift galaxies, only because we were able to detect the gamma ray burst, to have an efficient follow-up, catch this fading emission, doing absorption spectroscopy of this fading emission with very sensitive telescope, and so establish the existence and the redshift and also the position of these galaxies. So this means that gamma ray bursts are providing us a unique tool, a unique mean for detecting, localizing, and making a census of the bulk of the primordial galaxies that are invisible This means detecting invisible galaxies, galaxies that are below the detection threshold of the Hubble Space Telescope, of the VLT. And this will be true also in the future, of course, down to lower luminosity for the JWST, Extremely Large Telescope, and so on. So the gamma ray burst providing a unique tool to unveil the bulk of the population of the primordial galaxies. But not only thanks to gamma ray burst, we know the existence, how many they are, where they are, and at what ratios they are, these galaxies. But if we can use and point to this direction before the light fades away, a sensitive, very sensitive telescope, we can do also absorption spectroscopy, as I mentioned, which tells us not only the redshift, but also the properties of these invisible galaxies, the metallicity, as you can see, the neutral hydrogen fraction through the Lyman alpha absorption, and also the properties of the intergalactic medium. So of these invisible galaxies that we would never detect without a gamma ray burst, not only we know the existence, how many they are, the distribution, but also the metallicity, the neutral hydrogen fraction, and the intergalactic medium around them. Of course, this is outstanding capabilities of long gamma ray burst, very well known by cosmologists. But the main issue here is that despite the many efforts, observational efforts by many facilities in the space and on ground, we are still stuck with only a few gamma ray bursts detected at Rashi 6. So only a few gamma ray bursts actually have been now detected in the first billion years of the universe. So this is, as I will show later, one of the main goals of all the future gamma ray burst missions that are being studied by the worldwide community. So put here a statistical sample of several tens of gamma ray bursts in the first billion years of the universe. On the other hand, as I said, short gamma ray bursts have been demonstrated, as was conjectured by many since many years, as one or the main electromagnetic counterpart of gravitational wave signals. This idea that gamma ray burst, a fraction at least of short gamma ray bursts, could be produced by the merging of neutron star binary system or neutron star black hole binary system was put forward since many years. There were several evidences, for instance, the location. So why, as I said, the long gamma ray bursts are usually located in high star forming rate galaxies and in high star forming region galaxies, in their galaxies, where you expect that these very massive stars are located. Instead, you expect that these systems, neutron star black hole systems, are very old instead, are in the outskirts of the galaxies and are not directly connected to any kind of particular galaxy. And this is what is actually found. But in 2017, we had this, the final proof, a gravitational wave detected by LIGO from neutron star merging system, and the short gamma ray burst associated to this event. As you can see, there is a 1.7 second delay between the gravitational wave signal and the short gamma ray burst. I will get back to this, but this is, of course, is telling us something. This event was at 40 megaparsec distance, and this is already telling us that the first direct demonstration, if you wish, that gravitational waves travel at the speed of light, or at least if there is a strong limit. This puts a strong upper limit to the difference between the two velocities. As I mentioned, in association to the gravitational wave signal, it was discovered not only the short gamma ray burst, but the other electromagnetic counterpart, the Kilo 9 emission. So this is on the bottom left. These are the light curve of this fading optical near infrared source in different filters. These are simply near infrared and optical filters. So this was a rising and then decaying source. And on the bottom right, you see the spectrum, the spectral evolution of this source, showing many lines. And as I show here, on the bottom right, these lines were actually the lines that are expected if this emission is produced by the radioactive decay of very heavy elements being produced after the merger or during and after the merger, because of this very, very dense neutron-rich material through our processes. And this was supposed to be one of the main channel for producing these very heavy elements. in the universe, and this also was demonstrated. So on the left here you see simply a sketch on how this radiation is produced by or through the merging of two neutron stars, forming a black hole and accretion disk. There is then the launch or a supermassive, highly rotating neutron star, producing in any case a relativistic jet that produces the gamma ray burst, and also this wind, as you see, equatorial or polar, producing two-component emission in the near infrared that again is due to the mostly radioactive decay of these very heavy elements. So what can we do with this, putting together the gravitational wave and electromagnetic measurements for this kind of sources? Of course, we can get a lot of information and do many studies on the relativistic jet formation, a question of state of neutron stars, fundamental physics, again radioactive decay, so formation of very heavy elements in the universe, but also, as is shown on the bottom right, doing in turn also cosmology, multi-messenger cosmology, let's call it. Indeed, you know very well, as is shown on the left panel, there is this tension on the measurements of H0, with the CMB providing a lower value with respect to type 1a supernovae or other methods for the lower redshift universe. And of course, the idea here is that if you get again a statistical sample, in this case of gravitational wave signals with associated electromagnetic counterpart from which you can derive the redshift. So by modeling the gravitational wave signal, you get the distance of the source in a cosmologically independent way. And then you have the redshift from the electromagnetic counterpart. And so you can build the Hubble diagram, which is the distance as a function of the redshift. And you know that this relation depends on the cosmological model, on the Hubble constant, on the omega m, omega lambda, if you use the standard lambda CDM scenario, or on the evolution of the dark energy, and so on, you know, of course, very well. With a few tens of these events, you could really assess the value of H0, or even study the evolution, as is shown on the right, of W0, if you assume a standard parameterization of the equation of state of dark energy. This is what was done, you see in red here, the Hubble constant as derived with only one measurement. So the only one simultaneous detection that we have up to date, as I discussed, the gravitational wave and gamma ray burst detected in August 17. So of it, only one event, you could already have this distribution probability in the red line, peaking at around 70 for the Hubble constant. So in between the Planck and the lower redshift measurements. But then if you can get again several tens of these events in only 20 simultaneous detection between gravitational waves and electromagnetic counterparts, let's say GRB in this case, you could get this kind of constraint. So this is a kind of multi-messenger cosmology, very, very promising, of course. And this is just to mention that, of course, this link between gamma ray burst and gravitational wave sources is not only restricted to short, so to neutron star mergers, so to short gamma ray burst, because there are other possible sources, much more unlikely, much more difficult to detect by the current and near future gravitational wave detectors. But in any case, it is worth to mention that also core collapse of very massive stars, if the core collapse is asymmetric, can produce gravitational waves, for instance, or other extreme sources like soft gamma ray repeaters, which are produced actually by these magnetars, so hugely magnetized neutron stars. If actually these soft gamma rays emissions, bursts of soft gamma rays, are produced by quakes or instabilities of these neutron stars, which could also produce weak gravitational wave signal. So, given, as I mentioned at the beginning, these high potentialities of gamma ray bursts for the cosmology, for the multi-messenger astrophysics, of course, cosmology and multi-messenger astrophysics are the main goals of next generation missions and instrumentation for the study of gamma ray burst. mostly for the end of this decade or for the next decade. Also aiming at providing a huge synergy with all the very large facilities that are being built in the electromagnetic domain. As you may know, of course, we are in a golden era on the point of view of observational facilities. We are building or studying, already developing extremely large facilities in the optical, extremely large telescope, ELT, the TMT, in the radio, SKA, in the very high energy domain, so SKA or Athena, mission by the European Space Agency in the X-rays. And of course, the same is true for gravitational wave and neutrino detectors. This is the path for the next, the end of this decade and the next decade. We expect further advanced second generation gravitational wave detectors in the second half of this decade. So extending the horizon, the cosmic horizon at which we can detect, for instance, in gravitational waves, neutron star into star black hole mergers, up to a few hundreds of megaparsec. But there will be then a huge step forward with the third generation of gravitational wave detectors. This is for the second half of the 30s, very likely. And in this case, we will be able, as is shown here on the right, we will be capable to detect this kind of gravitational wave signals up to very high redshift. So this is the concept of this future gamma ray burst mission. I make the example of the TSIUS, Transit Energy Scanner Universe Surveyor. So this is an acronym, which was an European mission that has been studied by the European Space Agency, led by Italy. So I use this case, but this is the same concept that is adopted by all the other groups in the USA, in Japan, and so on. As I said, next generation missions for GRB aiming at full exploiting gamma ray bursts for cosmology and multi-messenger astrophysics and providing these great synergies with future observing facilities. So the concept here is, first of all, to extend the capabilities of current gamma ray burst monitor by extending the energy band down to the soft X-rays, up to the gamma rays, so to be and of course improving the sensitivity of this monitor, so to improve substantially the capability of detecting and localizing very high redshift, still keeping a very high sensitivity to short gamma ray burst and any kind of gamma ray burst. This is only a part of what we need, because of course, first of all, we need to detect many more high redshift gamma ray bursts, but we also need to know that these are gamma ray bursts at high redshift. How do we know? We know, of course, a measurement in the near infrared. As I mentioned at the beginning, it is thanks to the detection, localization, and spectroscopy of the near infrared afterglow, so the decaying light after the gamma ray burst, that we can identify the redshift, the host galaxy, and also characterize this host galaxy through absorption spectroscopy, the metallicity, the neutral hydrogen fraction, and so on. And to improve substantially, so to reduce the inefficiency, the current inefficiency in the process leading to the detection, localization, and redshift measurement of this near infrared afterglow that you need. The idea, of course, is to put directly a near infrared telescope on board and give the spacecraft the capability of autonomously following, so pointing in a few tens of seconds or a few minutes, this telescope in the direction of the gamma ray burst provided by the monitors. So the combination of this instrumentation and mission profile would allow this use and these missions, as is shown in this diagram, where you see the spectral peak energy, so the spectral hardness, versus the peak flux, so the intensity, the brightness of the gamma ray burst. So this combination of instrumentation and mission profile will allow this mission to detect any kind of gamma ray burst. So if you have a look on the bottom left side of the diagram, here there is the bulk of the population, of course, of high redshift gamma ray burst, which are expected to be soft and weak because they are redshifted, of course. And their emission is beyond the capability of current detectors, like the Fermi Gamma Ray Burst Monitor, the red dots here. and still keep the sensitivity to detect harder, so especially harder gamma ray bursts like the short ones for multi-messenger astrophysics. So to give an idea, mission like Theseus for the high redshift gamma ray burst, and so the cosmology with gamma ray burst, the early universe with gamma ray burst. This is the current scenario in terms of, on the left, luminosity versus redshift, and on the right, in a cosmic context. This is the situation. So as I mentioned before, despite the many efforts of many facilities from space and ground, in the last more than 20 years, we could detect only a few gamma ray bursts at 3006, the first billion year of the universe. With Theseus, you could instead get this kind of results. So improve substantially. These are the red dots, are the gamma ray bursts detected, localized, and identified as high redshift gamma ray bursts by the spacecraft itself. So clearly a huge leap. You will get several tens of gamma ray bursts at 3006 and hundreds of gamma ray bursts at redshift, lower redshift, with not only the redshift measurement, but also a full multi-wavelength characterization, which is fundamental for understanding the physics, the mission, and the progenitors of these gamma ray bursts. At the same time, such a combination of instrumentation mission profile will allow Theseus or similar mission to detect, localize, and characterize and measure the redshift of most classes of transients in the high energy sky. So in particular, as I mentioned before, those short gamma ray bursts, but also other possible X-ray emission associated to neutron star black hole mergers, which are up to now and will be also in the next years the bulk of the gravitational wave emitters that can be detected by interferometers on the ground. So just to give you an idea, this is again the observational scenario that we get in 2017 with again the detection of the gravitational wave from neutron star system, the short gamma ray burst, the kilonova emissions that in the near infrared that I already. And this again took the efforts of many facilities from space, from ground, many hours or days to take all this amazing observational scenario. And a machine like Theseus could do all of it by itself, detect and localize the short gamma ray burst, detect and localize the possible, the kilonova emission or the near infrared afterglow of the burst, and also detect and localize the possible soft X-ray emission that some models expect to be produced after the neutron-star merger if very massive, fast rotating neutron star and highly magnetized neutron star is left as a remnant of the merger. So really impressive capability. Here I would like to stress, as it can be seen here in this scenario, that as was demonstrated for this unique event, GRB 170817, that this very nearby gamma ray burst, short gamma ray burst associated to these neutron-star mergers that are within the horizon of a few hundred megaparsecs of the current and near future gravitational wave detectors are most likely detected off axis. So this emission is most likely collimated into a jet, and usually we detect short gamma ray bursts at threshold higher than 0.05, 0.1, not so nearby like 40 megaparsec. And if you are so nearby, you likely detect them very off axis. You see the gamma ray burst and their luminosity very low. You see them very soft because of course of Doppler relativistic Doppler effects. So the capability instead of these future missions, as I mentioned, will extend the detection of gamma ray bursts down to the soft X-rays, will unveil also the bulk of the population of local short gamma ray bursts associated to gravitational wave emitters seen off axis, which are again, these capabilities are beyond the current capabilities of current gamma ray burst detectors. And thanks to these capabilities, we expect several tens or hundreds of electromagnetic counterparts, short gamma ray burst, X-ray transients associated to gravitational wave signals detected, for instance, by third generation gravitational wave detectors like the Einstein telescope or Cosmic Explorer. So this is a sketch, a summary of what we can do with these multi-messenger observations. Again, here mostly focused on neutron-star black hole mergers. This is a summary of what I already outlined. So I can go on, and this again sketches the huge synergies that this use or similar missions will have with all the large, extremely large facilities of the future in the electromagnetic domain, but also in the gravitational wave. I mentioned also neutrino detectors because gamma ray bursts are also expected to be a major source of neutrino, even if this is still to be demonstrated. It has recently been demonstrated that they emit also very high energy, so TV photons, but of course, for neutrino, there is still no evidence. It is important to stress that all these facilities have gamma ray burst, high energy transients, multi-messenger astrophysics, cosmology with gamma ray burst in their core program, in their core science. So a machine like TSUS or similar mission is of course needed by these facilities to fully exploit their scientific capabilities. I would take a last couple of minutes to briefly go through what I would call as additional capabilities or assets of gamma ray burst. So what I described to you up to now are the commonly agreed impressive capabilities, or at least some of them, of gamma ray burst. But as I mentioned, gamma ray bursts are interesting, very interesting and very important phenomenon in modern cosmology and astrophysics and fundamental physics under several aspects. These are additional aspects. As I mentioned at the beginning, we can do cosmology with gamma ray burst not only with respect to the investigating the early universe, but also for investigating the cosmological parameters, evolution of dark energy, cosmological models, because there is a lot of activity in investigating correlations between, as I show here, spectral properties and the luminosity or radiated energy that are very promising for standardizing gamma ray burst in a way similar to what is done for type 1a supernovae, for instance, where for type 1a supernovae, it is exploited the so-called Phillips relation, so the relation between the peak magnitude in the light curve of this type 1a supernovae and the decay time of the light curve. Here, we exploit the correlation between the spectral peak energy, as you can see on the left, the typical spectra in new spectra of gamma ray burst have a peak, show a peak, and the photon energy at which there is this peak is called the spectral peak energy, which correlates, as you can see on the right, very well with the radiated energy and peak luminosity. So we can exploit this correlation, and actually this has already been done. There are many works, and this is a pioneeristic work that we did in 2008. What we did was to check if this correlation was dependent on cosmology. So if you could extract cosmological information from this correlation, and what we did was I go back to fit the correlation as a function of the value of omega m by assuming a flat lambda CDM scenario. We vary the value of omega m from 0 to 1, with which is computed the luminosity distance used to compute the isotropic related energy. So we created a correlation for each, a data set for each value of omega m, fit the correlation with a likelihood that is well suited for this kind of study, and evaluated the goodness of fit, the likelihood, or the chi-square. And what we found is that the goodness of fit, or the chi-square, or the minus log likelihood, as a function of omega m, has a nice parabolic shape, minimizing at omega m 0.3. So this means that if we didn't know anything about type 1a supernovae, but simply we assume a flat universe, as is direct evidence from only the CMB alone, and the main expectation, of course, from
how are we with time?
Okay, I'm concluding. So from inflationary model, from gamma ray burst, we have independent evidence that if the universe is flat, omega m is around 0.3, so the universe is actually accelerating. And this is a very powerful demonstration. Then you can do much more. You can have contours in the omega m omega lambda plane, as you can see on the bottom right, which are, this is the pink contour from gamma ray burst, already competitive with the contours from other probes. And this is what you will get, or we are getting, for the estimate of omega m as a function of the number of gamma ray bursts that we are building in the sample. So increasing the measurements will increase this potentiality of gamma ray bursts. So to conclude, I just mentioned that gamma ray bursts, because they emit over a huge energy band, so several decades in photon energy, they release a huge amount of photons, and the detectors of gamma ray bursts, at least a part of them, have a timing resolution of the orders of microseconds. You can use, as is shown here in this formula that you know very well, you can use gamma ray bursts to test the Lorentz invariance and hence to test quantum gravity or to put limits on the quantum gravity mass, because of course you exploit the delay between low energy and high energy photons. This was done, for instance, in this case of this very bright short gamma ray burst. Of course, here you can see in this table the limits, the quantum gravity mass with respect to the Planck mass that have been derived from these studies on gamma ray burst.
How are we doing with time? How long have you been doing?
Okay, this is just to mention. So as I mentioned before, another important clue for fundamental physics from gamma ray burst is the delay between gravitational signal and electromagnetic signal, as I mentioned before. So this 1.7 seconds already put a very, very stringent limit on a possible deviation between the two velocities. So it is a direct confirmation that gravitational waves travel at the speed of light. And this is my conclusion. So sorry for being a bit long. If you want more information on the Theseus missions, that is one of these future missions exploiting gamma ray burst for cosmology and multidimensional astrophysics, you can go to the website or read the many articles on the archive. So thank you very much. Sorry for being long. Thank you very much again. This is all.
Well, I've been following this talk, and in a certain sense, the Roman used to say errare humanum est, but perseverare, etc. By the way, I think the Theseus mission, I hope you have explained, was not selected by ESA. And I think your presentation is a very extensive and detailed presentation, which was the soul of the Theseus mission. And I think you and everybody else should take care of rethinking the validity of this, and we will keep this as a document of what your thought for Theseus was. But let me explain one point. We are doing all the effort possible to look at the data and the theoretical interpretation. Yesterday, we had an entire session about the problem of H0, which was really profoundly interesting, and not asking the help of solving the problem with 1708-17. Moreover, we are having a session still on the different interpretation of 1708-17. And all these pictures and things that you presented as given, we make a special effort in this MG16 to distinguish between things which are given and things which are the thing of interpretation, and focus on experiment that can clarify this situation, which is clearly sort of messy. Anyway, we will keep this presentation as an example of what a mission like Theseus was grounded, the mission. I thank you very much, Lorenzo, for this presentation, but I think we have to go on to the following speech.
Thank you very much, Remo, for the comments, of course. Thank you.
Okay, so we have no time to take questions. So our next to speak is Alina Pian. She's talking about the supernova of gamma ray burst 190114, please.
Yeah, okay, thank you very much, EFA. I will share my screen now. Let me try and see if I can succeed doing that. Yes.
Yeah, we can see you.
Okay. Okay, so thank you very much. So this talk will represent an overview of the state of the art of gamma ray burst supernova connection. And the final part of the talk will expand on this latest very interesting gamma ray burst. So gamma ray burst as already introduced by Lorenzo, so I will not dwell into this. They are very brief flashes of soft gamma rays that were completely, whose origin and nature was completely unknown until 1997. We now know that gamma ray bursts come in two flavors depending on duration and accordingly spectral hardness. So there is a majority of long duration, softer spectra gamma ray bursts, which we know are associated with supernovae, and a minority of short, hard gamma ray bursts, which we have learned recently are associated with binary neutron star mergers. And this talk will expand on will be concerned with the long gamma ray bursts. Here you see a view graph of isotropic gamma ray emission, the isotropic energy of gamma ray bursts, both short and long, as a function of redshift. The shaded orange area indicates roughly the subset of gamma ray bursts we will be concerned with, meaning long gamma ray bursts at low redshifts, because those are the gamma ray bursts that we can, where the supernova can be studied best, most accurately. So all of the examples I will show are actually at redshifts, definitely redshifts less than 1. So the prototype of gamma ray burst supernova is this object, supernova 98 BW, discovered on 25 April 1998. The characteristic of this supernova is that it's a so-called stripped envelope core collapse supernovae. Supernovae come in two flavors: thermonuclear supernovae, type 1, so-called type 1a, and core collapse supernovae, which are the final fate of very massive stars. So gamma ray burst, we know today that gamma ray burst supernovae are all core collapse supernovae, very much stripped envelope, meaning without hydrogen, without helium, and in their envelope, in their spectrum. So what's special about 98 BW? Well, first of all, it's very luminous. I will show in a minute its luminosity compared to other supernovae, but especially the very important thing is that it's very highly energetic. You know that kinetic energy in supernova of any type is around 1 beta, 10 to the 51 ergs. Well, 98 BW was 5, 10 to the 52 ergs, so 50 times more energetic than the average core collapse supernova. And you see the spectra reveal this very peculiar characteristic, this highly energetic character. As you see here in the bottom right is the spectrum of 98 BW at maximum light is compared with maximum light spectra of other core collapse supernovae. Basically, the spectra look physically the same, meaning the atomic species in all of these spectra are the same, just the absorption lines in 98 BW are so much broader than in other supernovae, and therefore blended, meaning the velocities, the photospheric velocities are very high. They generate blue shifts. The high photospheric velocity since the material is coming towards you, is generating a blue shift in the lines and a broadening of the line profile. And we are observing the lines we are observing here, just to give an idea of the atomic species, is lines of silicon, calcium, iron, definitely not the Balmer line. We don't see hydrogen and we don't see helium lines in this type of supernova associated with gamma ray bursts. This is what I was mentioning before. The lines, these are spectral series of this prototypical gamma ray burst supernova, 98 BW, from immediately after the explosion to late times. If you follow the same line, for example, silicon 2 at 6300 and angstrom 55, you see that the same line is seen very much blue shifted at early times, and as time goes by, the blue shift decreases, and accordingly, you can derive a photospheric velocity, as you see here on the right. And here are the photospheric velocities of many gamma ray burst supernovae. The top 5, the red ones, are gamma ray burst supernovae, compared with photospheric velocities of other core collapse supernovae as a function of time. And as you can see, gamma ray burst supernovae have higher velocities than any other core collapse supernovae, and these velocities at the beginning can reach astounding values that are higher than 10% of the velocity of light. So we are speaking of very extremely high velocities. Curiously, rather significant gamma ray burst supernova, represented here by the star, supernova 2013 DX, that one is not very extreme, and I will show it's quite luminous, it's quite prominent, but its velocity and therefore kinetic energy is not as high as the others. This is a comparison of luminosities. This is the 98 BW that I mentioned before, very luminous supernova, more than a magnitude, more luminous than other supernovae, than core collapse supernovae. And the only supernova here in this view graph that is not connected to a gamma ray burst is 1994I, here in turquoise in the bottom, and as you can see, it's a dwarf with respect to these powerful gamma ray burst supernovae. And here is a comparison, it's a bit more physical view graph, is a comparison of relevant physical quantities of these objects. On the left, you see the ejecta mass in various core collapse supernovae, including gamma ray burst supernovae, as a function of the kinetic energy. And as expected, predictably, gamma ray burst supernovae occupy the top right corner of this view graph, meaning they represent the higher energy, higher mass tail in the distribution of all core collapse supernovae. And here it's highlighted 2013 DX, for which the kinetic, that doesn't land in the same locus as the other gamma ray burst supernovae, and because of its kinetic energy. Otherwise, it's very similar. Its properties are similar to gamma ray burst supernovae. On the right, you see the nickel mass of these supernovae as a function of progenitor mass. We are speaking of, in general, in core collapse supernovae, we are speaking of progenitors higher than 8, 10 solar masses. Well, gamma ray burst supernovae have progenitor masses that are at least 30 solar masses. And the nickel mass is accordingly higher, namely these supernovae are more luminous than the average. There is a little note to be made about a special case that was detected some years ago, supernova 2008D, which is was seen as it's a core collapse supernova, was associated with an X-ray, with a high energy event, detected in X-rays, but not energetic enough to have the dignity of a gamma ray burst. It's let's call it an X-ray burst, an X-ray flash, whatever. Its energy is 10 to the 46 ergs, which, as you can see, compared to classical gamma ray bursts, 10 to the 46 is not even included in this view graph. It's too low in energy. So the energy of this event was definitely weak. It was associated with this supernova that you see here. There is the bolometric light curve in black compared to 98 BW, compared to other core collapse supernovae, gamma ray burst supernovae. It's quite weak. It's relatively less luminous. The interesting thing about the supernova was the spectra. There is as you can see here, there is an initial peak. If you look at the light curve, the black points, there's an initial peak around 4 or 5 days. And then there is a second much more luminous peak, which is the classical one typical of all supernovae. So the first peak is probably what is called a shock breakout emission. It's the emission that comes out in all wavelengths in optical, ultraviolet, infrared, and then cools. It's the emission. It's not that it doesn't have a radioactive origin. That luminosity is just cooling of a shock, of the supernova shock, as it breaks out of the stellar envelope, out of the stellar surface. And so a spectrum taken there at the peak of this shock breakout of this early emission shows broad lines and no helium as a typical gamma ray burst supernova. Very curiously, at the time of the maximum, meaning at 20 days, helium lines are developed and can be observed. So if this supernova had been detected just like every regular supernova, after, like, starting from day 5 or day 6, after a week, for example, it would have been detected as a helium supernova, namely as a type 1b supernova, not as a type 1c supernova, not as a stripped envelope supernova. So this circumstance, the fact that the associated X-ray event is so weak, has so low energy, and the fact that helium lines are observed, which is very unlike supernovae associated with high energy events, made us think that there is a correlation between having helium lines, this circumstance, and producing only a weak event. Namely, if you have a significant envelope, meaning there is a helium mass, a helium layer of significant mass left over around the star when it explodes, a powerful relativistic jet cannot form. So you only see a midget, you only see a very tiny X-ray event. You don't see gamma rays. This is not a powerful, a fully fledged jet. So a special chapter is deserved by ultra long gamma ray bursts. These are a minority of long gamma ray bursts. As you can see here, is the same view graph I've shown before. The duration of long gamma ray bursts is around, the majority of long gamma ray bursts range between 10 and 100 seconds. Well, long gamma ray bursts are much longer than this. They can be a few hours in rest frame. And it has been discussed what they are. I mean, do they belong, are they the same machine, have the same progenitor, same mechanism as long soft gamma ray bursts? Well, the debate persisted. Here you see a prominent long gamma ray burst, 11-1209. The debate persisted until a counterpart was detected for one of these long gamma ray bursts. And you see here the light curve, the optical light curve. There is a detailed optical monitoring of this gamma ray burst, and the afterglow was found. Here you see here the decaying, the monotonically decaying afterglow, and then there is a bump in the light curve. That's the supernova. So let's go a little bit into some detail in the supernova. A spectrum was taken around the maximum of the alleged supernova. It's definitely a so it's shown in blue here in this view graph. It's definitely a supernova spectrum. Just it doesn't look at all like supernova 98BW. It is much more similar to the spectrum of superluminous supernovae. These superluminous supernovae are a subgroup of supernovae that has been relatively recently detected. They are truly superluminous, much more luminous than core collapse supernovae, or than regular supernovae for that matter. And this supernova 11KL associated with this ultra long gamma ray burst is more similar to those superluminous supernovae than gamma ray burst supernovae as we knew them before. You see here a comparison of light curves. At the center, you see in blue the supernova 11KL, which is intermediate in luminosity between superluminous supernovae. Here you see a couple of them, two representative ones, and gamma ray burst supernovae, 98BW or 6AJ. And the peculiarity, the interesting aspect of this supernova is that if you fit the light curve with nickel 56, just with purely radioactive mechanism, you need a lot of nickel 56, like one solar mass. But one solar mass of nickel 56 would require a much more severe suppression of the blue part of the spectrum, which is not observed. This spectrum is suppressed in UV, short of 2000 angstrom, 2500 angstrom. But the near UV and blue part of the spectrum is still very bright. It's not suppressed at all. So we suspect that there's something strange here, that there is some incoherence, which leads us to believe, to suspect that that the culprit, the responsible mechanism for luminosity cannot be ascribed to nickel 56 only, but there must be some other component which we tentatively identified with magnetar energy, meaning with the energy of a rapidly millisecond neutron star, highly magnetized neutron star, promptly formed neutron star. So this would be different from regular gamma ray burst supernovae, where we think that the final remnant, the central compact remnant is a black hole. So this is to give you an idea of supernova. It's a synoptic view of superluminous supernovae, just to put in context, to understand what we are talking about. Superluminous supernovae on the top of this view graph are compared with any type of previously known supernova, 1A in green, in turquoise, in light blue, and then black and green, light green is core collapse supernovae. So our 11KL supernova is here in between. It's at -20, absolute magnitude -20. Here is the top, the maximum is the -20. So it's truly in between. It's a gap. It's a bridging object. It's an object bridging the gap between superluminous supernova and every other type of known classical supernova. So we finally come to our object, the subject of this talk, which is the first gamma ray burst detected at TeV energies. This is the TeV sky, as we knew it until the detection of 190114C at an intermediate redshift, 0.4. 0.42 is definitely a low intermediate redshift for gamma ray bursts, since we know them, we know they explode, we've seen them exploding up to redshift 9 or 10. So this is definitely low redshift. But obviously for TeV detection, you do virtually need something at low redshift. And this is the light curves of the swift and magic light curves of the prompt event. So in light green is the swift but light curve of the gamma ray burst, and in red is the magic detection. And in blue here on the bottom, you see for comparison the TeV level of the Crab Nebula. This is to give you an idea of the amount of power these objects emit in at TeV, so beyond 0.3 TeV. This is the this is the isotropically radiated energy in gamma rays. It's a very respectable gamma ray burst, not one of the most energetic, but still very respectable. in gamma rays. This is a view or a view graph of the multi-wavelength follow-up, multi-wavelength light curves of this object between radio and TV. There's virtually all frequencies in this view graph, light curves at all frequencies, and notably also in optical. You see them here in V band, R band, K band. So optical infrared are the green and purple little squares. So we see here, yeah, a better view of the optical. This view graph shows our own monitoring, which is published by one of our collaborators, Andrea Melandri. And this is the optical light curve that we have decomposed into a non-thermal, monotonically decaying afterglow and a supernova, shown as the turquoise pentagons. So the supernova, you see better here the light curve, the bolometric light curve of the supernova. Bolometric is a bit of an iffy definition here because this object doesn't have many data. We couldn't follow it up in many bands. So bolometric here actually refers to 3,000 angstrom between 4,000 and 7,000. So it's pseudo bolometric. In any case, the light curve, the bolometric, the overall light curve of this object is a little bit uncertain because it depends very much on the afterglow subtraction. So depending on how bright the afterglow we assume to be, you have two limits, two boundaries for the bolometric light curve of this object compared with other known gamma ray burst supernovae. So it can be as bright as 98 BW or lower or less luminous. And we definitely think that the most plausible light curve, most plausible case is actually the yellow circles rather than the orange circles. Namely, our object is more similar to less extreme gamma ray burst supernovae than 98 BW because the spectral appearance is definitely different from 98 BW. You see here in the panel, the top panel shows the same spectrum of this object in gray, in black and gray. So there are two because they are obtained under two different assumptions of the afterglow level, afterglow emission. If compared with 98 BW, definitely you don't see any similarity. While the same two spectra are more exhibit lines that are more similar, have similar widths to less extreme supernovae, core collapse supernovae like O6AJ, O4AW. So very remarkably or curiously, although this object, this gamma ray burst is TeV, emitted up to TeV energies, the accompanying supernova is not one of the most extreme objects. And this is interesting. So I have my summary of the ideas I have presented here. So it's been in fact more than 23 years from the detection of the prototype gamma ray burst supernova. And all of gamma ray burst supernovae we've seen so far, including those for ultra long gamma ray bursts, have rather large quantities, extreme properties with respect to the bulk of core collapse stripped envelope supernovae. The correlation that they exhibit a range. They are generally high in every property, but they exhibit a range. And curiously, we don't know how this range, how these properties correlate with those of the gamma ray burst properties themselves. There is no clear correlation. It seems that lack of hydrogen, the lack of a thick hydrogen and helium envelope is a condition to form a successful ultra-relativistic gamma ray burst jet. Ultra-long gamma ray bursts are potentially very interesting. Unfortunately, we have detected so far only one case. This is due to the intrinsic difficulty of detecting, the technical difficulty of detecting these ultra-long gamma ray bursts. They are associated with possibly the fainter tail of superluminous supernovae. And finally, supernova 19 JRJ associated with the TeV emitting gamma ray burst 1901 14C, the first known TeV gamma ray burst emitter, is a an interesting object, is probably as in the ballpark of gamma ray burst supernovae for what concerns the luminosity, but not as energetic. So thank you very much for your attention.
Thank you very much, Elena, for this beautiful talk and so rich of information, and presenting also the problematic which is clear between GRB and supernova, which appear diametrically opposite, in the sense that the supernova, the more we look at them, and we will present tomorrow 25 cases, including GRB 190114C, 25, they are practically the same peak luminosity, all 25 associated with the GRB. On the opposite case, the GRB instead are differentiated in three classes between 10 to the 52 and 10 to the 54, the 10 to the 48 to 10 to the 52, and below 10 to the 48, three different classes. But what is really incredible is that though the energy of GRB are very different, the luminosity of the supernova are the same. Therefore, this shown also in your presentation when you go from 98 BW, and you pointed out the difference with the structure of the supernova from 190114C, but we beg to understand why there is such a difference. Tomorrow we are going to attempt that. And the paradox is that the responsible for the different GRB, if you take into account the binarity, is still the supernova, that same supernova, but the condition where it acts are very different. And therefore, your presentation has been beautiful as usual, but also focusing on this paradox. And we will address this paradox tomorrow. Let's see if there are other questions. I'm sure they are, but let's see. Gregory, there are other questions?
If you see the question answer, maybe Elena can go and answer directly. Can you open question answer?
I think, yeah, I can, yes. So 2011 KL could also be a tidal disruption event. Yes, okay, misidentified as a supernova. Yeah, can I answer? Can I just say a word? Can I answer?
Yes.
Okay, so yeah, I would say the spectrum is quite revealed the blue here. The spectrum is a supernova spectrum. Anyway, it's similar to superluminous supernovae. Anyway, it can be, we can do, I mean, one can discuss in a better detail, but we have also identified the typical lines. So yeah. Is it safe to believe all core collapse supernovae and gamma ray burst connections correspond to supernovae 1C? Yes.
Yes.
Yeah, yes, definitely. Wherever we could study the spectrum well, which is not a given, you need to be at very low redshift. You need to have a very high quality spectrum in order to identify atomic species. When you are in that condition, which is you need to be at redshift less than 0.2. If the redshift is no larger than that, you can identify atomic species. In those cases, you never see hydrogen, you never see helium, except in this very peculiar case, which is not, technically speaking, a gamma ray burst. So yes, the lack of hydrogen and lack of helium is a distinctive sign, distinctive characteristic of gamma ray burst supernova. And it's related to the bareness of the exploding stellar cores, which make it possible to launch a powerful, relativistic, successful jet. Are ultra-long gamma ray bursts and superluminous supernovae conceivably related? I don't know. All I can say is that in Jochen Greiner's 2015 paper, we have argued that the possible role, partial role of a magnetar may help making both part of the luminosity of the supernova, of the superluminous supernova, and make an ultra-long gamma ray burst. I don't know so I'm not sure we have other elements to expand on this, to elaborate on this. Unfortunately, that's the only case. It's an isolated case. So we don't have much, we don't have a sufficiently solid benchmark with only one case.
I think we should end this talk. If you have any other questions, you can type your questions in the question answer box.
Sure.
And also Lina can answer your question by typing.
Sure.
Okay. So I think you should end, stop sharing your screen.
Yeah, sure. Let me do that. Stop share. Yes. Okay. Thanks.
Oh, thank you. So the last speaker of block 1 is Carlos Revulas. Are you ready?
Hello. Good morning. Yes, I'm ready.
So yeah. Yeah, we can see your screen.
Yes, but I have to move this bar here in order to. Oh, yeah.
You can show the full screen.
Yeah.
Yeah, perfect.
Okay. Good.
Yeah, you can start.
Yes. Give me please 1 second. I want to hide this bar in order to don't. Well, we put it here. Okay. Good morning. Thanks. Thank you. Now I will change topic a bit. This talk is about dark matter in the Milky Way. So it will do mainly to dark matter, but also it will be related to the central galaxy center, the central ocean in our galaxy, Sagittarius A star, and but also to massive black holes, as you will see in a moment. So this talk was on the works. This talk is based on the works here you can see below. It's a series of papers we have published in the recent years with our collaborators from ICRANet mainly, Remo Ruffini, Jorge Rueda, Andreas Krut, Edward Becerra, and Rafael Yunis, also my student. Okay, let me start with the outline of the presentation. First, I will introduce some preliminarities about cold dark matter. Then I will move from blasts of Poisson to cell-gravitating fermions as dark matter halos. Then I will show the case of the Milky Way and the galaxy center. Then I will move to universality of fermionic profiles. And lastly, we'll introduce the concept of critical core mass and supermassive black hole formation from dark matter. Then I will conclude. So let's start with a bit of contextualization of this talk. So this talk will have to do with within the particle paradigm of dark matter. So let's assume you have a neutral fermion generic dark matter candidate, which was created just after inflation, and that decoupled from primordial plasma in the first fraction of a second prior to photon decoupling, and then due to the primordial density fluctuations, and the expansion and cooling of the universe, these fluctuations grew, and it generated the seeds of dark matter halos that then will act as a potential wealth for baryonic matter and lately galaxies as we see today. So these generic dark matter candidates are the basic hypothesis is that it is cold and collisionless fluid, and it has been given a very successful consequences for cold dark matter. So we can say that astrophysical observations such as CMB, DAO, Lyman alpha forest, and the local distribution and evolution of galaxies, ranging from horizon scales to the typical scales between galaxies, are all consistent with a universe that was seeded by a scale invariant primordial spectrum, and that is dominated by dark energy, followed by dark matter, 25%, and only roughly 5% of baryons plus radiation. So this is what is called the lambda CDM cosmology. And as we have seen yesterday in the beautiful talk of George, that from cosmological perturbation theory, so the theory that describes how primordial density perturbation grow into galactic structures, gives this beautiful CMB anisotropic distribution. For example, for temperature distribution, which was measured with a precision of 1 in 10,000, remarkably, and one of the many consequences. But regarding dark matter, one of the strongest evidence for dark matter is that in order to explain the temperature fluctuations in the Bauer spectrum, you can demonstrate that these peaks in the spectrum are very sensitive to the amount of dark matter. For example, this is a qualitative example where you see that as soon as you decrease the amount of dark matter, the relation between second and third peak changes. And also, if you increase the dark matter, also the height of the peaks and the positions also shift. So this is out of this CMB data and lambda CDM cosmology, we can say there is a compelling evidence for non-baryonic matter in the CMB. Okay, so now let's move, as will be the main topic of this talk, let's move from large-scale structure to dark matter halo-sized structures. Therefore, this is a picture in the left to the Sloan Digital Scar survey of some years ago, where you can see that in the local universe, the distribution of dark matter is not homogeneous, but is in a form of a cosmic web with these beautiful filaments, nodes, and voids. And these are images of a huge amount of galaxies that cluster in this way. And interestingly, this kind of distribution, of local distribution, has been updated recently by the DES survey, the Dark Energy Survey, which reached to make photograph of more than 100 billions of galaxies, superseding these nice distributions. So when you point into a node and into an object inside this cosmic web of the size of a halo, let's say 100 of kiloparsec, you have this a picture of a dark matter halo arising from simulation in this case. And then we can see the role of dark matter in the halos, as you probably heard, that it implies generally that the rotation curve, so the circular velocity of stars around the galaxy, do not follow the expected Keplerian behavior in the outer parts due to baryons, but instead remains constant in a certain window of radii, showing the need of an extra matter component, which is not emit light and is roughly spherically distributed, ranging around an order of magnitude larger than baryonic matter. Okay, so now let's move a bit to some mathematics and how we can explain or attempt to explain these dark matter halos in terms of spherical distribution of fermionic particles. So let's start with the assumption of collisionless particles. So is dark matter, we can think of a collisionless system described by mean field Lasso-Poisson equation, which is this equation here, where is in terms of mass density phase space, so a phase space density F, which is a function of position, velocities, and time, and is coupled with Poisson. So you can see here the F is coupled with the Laplacian of the gravitational potential. And interestingly, this Lasso-Poisson equation, which is in terms of fine-grained density phase space, can lead to an coarse graining, can make a coarse graining where the distribution function is separated into an average plus density fluctuations, fine-grained density fluctuation, F tilde, and then you replace, and you can show this equation with the left-hand side resembles the Lasso-Poisson, but then in the right-hand side appears a diffusion current where we have put all the fine-grained fluctuation averaged. And so what we'd like to solve, which is the most likely distribution function at coarse-grain level at equilibrium due to self-gravity. So one way to do this, because this is a difficult task to solve these equations, because you have to know the microphysics of the fine-grained fluctuations. But a good way to proceed is to ask this effective diffusion current to fulfill macroscopic constraints, just a first and second law of thermodynamics, so energy conservation and entropy maximization. This is a form of a Lindenbell entropy, which when maximized, it tells you about the relaxation of the system. And this is a maximum entropy principle, which was shown in the original work of Chamonix in 1998. And so the key point here is that during this evolution, the system maximizes its rates of entropy creation while satisfying the contrarified field by the dynamics. So this is so-called the maximum entropy principle. So if you mix this entropy principle with quasi-linear theory, you can, as shown here, you can also write this coarse-graining kinetic theory equation and put in the form of a modified Landau equation, which allows not only to obtain the expression for the current and calculate the relaxation time scale, which in these cases, the collisionless relaxation time scale is much smaller than the collisional relaxation times, and allows you to find a most likely coarse-grain phase space distribution at relaxation, so stationary, when J is constant. So interestingly, the form of this phase space distribution of particles at relaxation is of the Fermi-Dirac type. You can recognize here in the denominator this Fermi-Dirac type, and the numerator has a cutoff in energy, saying that for energies of particles above cutoff energy, you don't, your particles, it talks about the evaporation of particles above a given energy. Interestingly, this stationary solution is a generalization of the traditional Lindenbell distribution function found in the beautiful work of 67 about binary relaxation. including for particle evaporation. Therefore, as you may remember, the Lindenberg theory was developed for classical particles, but it was extended also to include indistinguishable particles, such as neutrinos or fermions more generally. And in the case of fermions, therefore,
Yes.
In the case of fermions, the maximum accessible value of the distribution function, eta 0, is fixed, of course, by Pauli principle, which shows you that the maximum phase space density proportional to the particle mass to the 4 inverse to the HQ. Therefore, once we have a most likely phase space distribution of particles, in this case of fermions, at relaxation in a halo, we can proceed to solve which is the more general solution at equilibrium, the profile, the mass distribution at equilibrium out of this distribution. So first important concept is that fermions under self-gravity do admit a perfect fluid approximation. This was demonstrated in this original paper of 69, Rufino and Bonassola. Therefore, we proceed to solve the Einstein equations for a semi-degenerate gas of fermions in hydrostatic equilibrium, so these Tolman-Oppenheimer-Volkoff equations in spherical symmetry. So here is just a sketch of the equations in dimensionless form. But the important point here is to see, well, the first, of course, is that these are Einstein equations, first and second, the only two relevant Einstein equations in spherical symmetry for this distribution. So the mass equation, the TOV equation, probably you recognize, and the third, fourth, and five are Klein-Tolman conditions of isothermality in general relativity and energy conservation in geodesics. So you have to couple this Einstein equation with the source, so with the equation of a state, with density and pressure, which are written in terms of the integrals of the phase space distribution, which is this of Fermi-Dirac type, which this has to be thought at Kurzweil level, which is exactly the one I showed before out of relaxation mechanisms. So one important point is that this equation of a state is not barotropic, is parametric equation of a state, where the system pressure will depend on the free parameters such as the temperature of the effective temperature of the dark matter, the degeneracy, and the cutoff energy. The energy here is genetic energy, which is written relativistically, but depending on the regime you are, it can also go from non-relativistic, but also allows for relativistic regimes. So as you can see, this is a system of coupled, highly nonlinear, ordinary differential equations, and you have to solve for boundary conditions. So for a mass at the center, regular mass at the center, not singular, central degeneracy, we will search for solutions larger than 0, because the degeneracy lower than 0 goes to the traditional pseudo-isothermal sphere solutions. And well, given temperature, a given cutoff parameter. And this theory has 4 free parameters, which is the particle mass, the temperature, the degeneracy theta, and W, the cutoff energy, which we have to give at the center of the configuration. This is a boundary condition problem. So once you have the full system of equation, you can find that the most general solution out of this equation with boundary condition, with fixed boundary condition in agreement with halo observables, for example, in the case of a typical spiral halo with typical halo scale length of 10 to the 4 kiloparsec and halo masses of 10 to the 11, which is roughly here. With fixed boundary conditions, you can find, for example, a solution like this. You can see here the main feature of this solution is that at the center, it develops a dense and degenerate core of fermions, which uses the Pauli principle in order to reach this highly degeneracy concentration, and then continuously goes to Boltzmannian tail. So the central, in such a case that the central object is support against gravity by degeneracy pressure, while the outer atmosphere of fermions is support against gravity by thermal pressure. Interestingly, at the scales where most data are in far galaxies, the slopes and the distribution of the profile. Well, of course, our profile are curved towards the center instead of cuspy, but in these windows of radii, all profiles such as called as a NASTO or either Barker or NFW coincide more or less at this scale. But the important point or the important question here is which is the role of this high density concentration of fermions here? First of all, it's important to say that this satisfies the quantum condition, so it can be checked for all solutions with degeneracy larger than 10, and the thermal de Broglie wavelength is larger than the 3 times interparticle mean distance, so satisfying the so-called quantum condition. And importantly, the dark matter profiles, mainly the feature of the course, will depend on the particle mass. This is an example. Typically with particles of 10 keV, you obtain this dense concentration. We start to fall inside the milliparsec scales. Okay, this is up to now the generic solution of these equations of, say, gravitating fermions, and then we proceed to apply to the best known case that we have, which is of course our galaxy. So first, let me introduce some preliminarities about our galaxy. So the central parsec is governed by, as you know, by a dark compact object of roughly 4 million solar masses, presumably a black hole. Then the central kiloparsec governed by an inner and main spheroidal bulge. And then when we move to 10 kiloparsec, the dynamics and kinematics governed by a flat disk or well, with some thickness, depending on the model. And in the outer region, of course, we have an extended dark spherical halo with a mass of 35 kiloparsec, roughly 10 to 11, as constrained by observation. So in the panel of down here right, you can see the data of the rotation curve showing this approximately flat regime in linear scale here. Above, as you can see, this is from 2013, but above, let's say, a few tens of kiloparsec, the error bars start to increase considerably. And this is a nice picture in the left, bottom left, in the logarithmic, showing that for the first time in the work of the world expert Sofue, he was able to link the kinematical tracers from a few parsec, so in the inner bulge of the galaxy. This is the peak of the main bulge. This is the inner bulge. Of course, the error bars here are larger because are showing the non-purely circular motion, because there are also a bar, as you may know, at the center of the Milky Way, but this as a defective circular rotation curve accounting for the non-circular motion, and well, here extended the rotation curve. So besides this data of the rotation curve, we can also look to the innermost first milliparsec of the Milky Way, and as you see here in the picture of the left, which is the S-star cluster, because the central region of our galaxy between milliparsec and few parsec consists of these young S-stars and molecular gas, following mainly in average a Keplerian law. So it has to be dominated by a very high mass and compact object. And interestingly, besides these beautiful S-stars, with very precise data as shown, which led to the Nobel Prize of last year, from either from the European and from the American teams, showing resolving with high accuracy the motion of these stars. It also, I will also include the G2 object, which first was, this G2 object is not fully well understood object yet, but first was thought to be a cloud, which orbits very nearby the center, Sagittarius A, with a pericenter very close to S2 star, which is one of the closest. And showing this, this is a simulation, the observation showed some stripping of mass around the when passing the pericenter, and either is the nature of this object is still discussed. It is more or less accepted that they should be not be of a gas, purely a gas, but it should be of a stellar composition, probably with some lost mass, because the main discussion here of C2, let me say, is that if it is assumed to be only a gas cloud, then it should have been completely ripped off when passing through the galactic center, as the most refined simulation has recently shown. So, as you know, the best object to constrain the central mass in the center of a galaxy is the S2 star, constraining a central mass roughly of, well, this is a bit outdated value, 4.2 10 to the 6 solar masses within the first milliparsec, but now values are more roughly about 4.1 10 to 6. Okay, so the challenge here is to use all this data, so the outer part of the rotation curve, but also the inner bulge data plus the S-star data, the precise measurement, and ask if these core halo profiles arising from relaxation mechanisms for fermions can, the potential can explain this rotation curve as well as the dynamics of S-stars without introducing the black hole hypothesis. So this is a fair question to be asked in these kind of profiles. And of course, you have to, a hint is that you have to solve the boundary condition problem, fixing these known values from observations, which you can fix at the center, the core of this dark matter. You can fix with the mass of the central object, and two other values in peripheral observations, either at the intermediate halo scales or also at outer halo scales, by, for example, by Sagittarius dwarf galaxy, in order to constrain the outer part. So all this data is used, and very remarkably, so it is possible to obtain generic solutions, a family of solutions. I show here in black core halo profile of fermions for a particle mass of 345 keV, down to the core halo profile in dashed gray for particle mass of 48 keV. So this particle mass range, because a key feature of this profile is that the larger the particle mass, the more compact and dense is the central core, until you reach the critical value of collapse due to the field degeneracy reached by this core. Therefore, it's interesting that that you can find a family of solutions for particle masses around 10-ish of 100 of keV that not only matches the full rotation curve of the galaxy. Of course, here you have to add the standard bulge in green and disk in dash green contributions, but also in this plot here, I show the eight best resolved S-stars in average circular velocity, where you can see that this high compact dark matter core is inside the pericenter of one of the closest stars with this S2. Therefore, so it is possible to make this fitting, as I have shown here, and this is a zoom of the outer part of the rotation curve, given by either NFW fit in black and our model in red. So both can fit very well the outer rotation curve. But then this is, we can go further and ask, well, can not only the average circular velocity of these stars be fitted or be reproduced without the black hole with this core, but also the geodesic or the orbit or the full astrometric data of S2 and G2. So we have done this work recently, and so let me first clarify the data that must be reproduced here. So there is a large amount of very precise data from BLT, Keck 1-2, Gemini North, and Subaru, had led to a multi-year accurate astrometric data of S2 star around Sagittarius A, including for relativistic redshift, as was found very recently or are shown to be the case for S2 star in gravity collaboration. And but also I have to be able to fit the most currently available data of the orbit and redshift of the G2 object, which was also possible to be detected. And also the G2 post-pericenter passage deceleration, which in the case, in the paradigm of the black hole, was explained in terms of a drag force. Okay, so let's start with the S2. So the S2 orbit, here I show in these gray dots all the astrometric data of rate ascension and declination of S2. And in red, you can see the best fit of our model of dark matter, how the central core reproduces these dynamics, and in blue, the black hole. So these models are calculated by solving the geodesic equations of test particle in the gravitational field, either of a Schwarzschild black hole of 407 10^6 solar masses, and this is the average reduced chi-square, this is the statistic of 3.3. And in the case of fermion core with a particle mass of 56 kiloelectron volts, we are able to fit this data with a similar reduced chi-square, even statistically preferred. Now, let's move to the radial velocity in the line of sight of S2. So now, first was the astrometric data, rate ascension, declination, and now the radial velocity of S2. So you can see this typical curve of radial velocity with the star is approaching to us and what is preceding us. And here is the data from, as you can see, more than 20 years in the 1994 first data until almost today, when S2 passed 2 times of pericenter, 2 times pericenter passage. And we can see beautifully that the redshift excess, so this redshift excess means the difference between the total radial velocity of the stars minus the Keplerian, the Newtonian contribution. So if this difference is larger than 0, it means that there are relativistic contributions to the Keplerian radial velocity, and this is the case which was confirmed a few years ago by gravity collaboration in red for the black hole, sorry, in blue for the black hole, and this can also be equally reproduced in red by our dark matter core. So this relativistic redshift can also be reproduced. Now, but more interesting or intriguing is now the case of the G2 object, because of course, G2 object has an orbit which is larger in size, and the period is for S2 is around 16 years, while for G2 is quite larger, and therefore it cannot complete an orbit yet. So here is the data, and we again calculate the geodesic equation of a test particle in the gravitational field of a Schwarzschild black hole and the dark matter. And interestingly, when combined the fit with the radial velocity, here now is the case for radial velocity in the line of sight of G2 with this astrometric data, we found, was very surprised, and we were very shocked to see this fitting, that for the same particle mass of 56 keV that you fit the precise astrometric data of S2, you can fit very well the post-pericenter passage, as you can see here, this 3-point after pericenter passage of G2, while in blue is the black hole model, that much better than the purely black hole, Schwarzschild black hole. You can see here the reduced chi-squares. In the black hole is 26, one in our case is close to 1. And so without the need of a drag force. So in the case of a black hole, this was explained by invoking a drag force with an accretion disk, though in extrapolating the physics of the accretion disk towards central regions where yet the environment physics is not well known, But by tuning some parameters, it was possible. It is possible indeed for the black hole paradigm to fit this data. However, the way it was done, it was needed to assume a gas cloud nature for G2, which is quite discussed recently. So there are different works suggesting that G2 should not be a gas cloud, but of a stellar nature, because otherwise it would have been ripped off by pericenter passage. And therefore, we find very intriguing that without the need of a transport, it is possible due to the continuous atmosphere around the core of dark matter, which cause a gradient of gravitational potential, generating these change in accelerations, able to fit this data. Very recently, we have extended our analysis and took the 17 best results as stars with the few data provided by the telescope I mentioned before. And by repeating the same procedure, we were able to also provide very good fits for all these 17 orbits. In red is S2. Well, the average chi-square, including right ascension declination and radial velocity of all the stars. In the case of a short-wave black hole is 1.5, while interestingly the dark matter case is statistically similar or equivalent, but sorry, in the case of RAR is 1.5 model. In the case so a bit statistically preferred slightly than respect to the black hole, but statistically, let's say, equivalent. It was shown recently in this paper and published in Notice letter, where we say here that for these 56 Kev fermions, you can have reproduce these dynamics together with the S2 and G2 objects. Okay, now in the last part of the talk, I will move fast to what about the universality of this profile. If you can apply for same particle mass, this core halo distribution to other galaxy types, from dwarfs to ellipticals to galaxy clusters. Well, we have attempted this phenomenology and have shown that, for example, taking the 8 best result Milky Way satellites, but also a sample of nearby things sample and some ellipticals by wheel lensing, so we can have observational well constrained mass and radius at the halo scaling radius, these green dots, and have explored the full family of solutions of dark matter profiles that are able to match this data to show that there are a family of possible degenerate cores of dark matter. We are able to fit this data, and interestingly, it can be shown, for example, in the case of dwarfs, that the core masses, yeah, here this is mass in the upper plot is mass in the y-axis and radius in the x-axis. You can see that mass of the core ranges from roughly 10 to 4 up to 10 to 6 solar masses. So it's a nice natural indication of intermediate mass in black holes, but not collapse, but in terms of interpreting in terms of high density cores of dark matter and not black holes. In these spirals, the core masses rises and goes from 10 to 5 up to 10 to 8 solar masses, up to the typical masses of active galaxies, and the same for larger elliptical. So we have further tested the correlation of these central core mass, halo mass, which there are correlations from data, which is this Ferrarese correlation. So Ferrarese not only have shown the more maybe known as M sigma correlation relating the central object mass with the bulge mass, but also correlations really for large galaxies, sorry, relating the central object mass with the halo mass. So this is shown in this strip here, light blue strip, and we have in the full coverage of our parameters, we have shown that there are always families of profiles that can match this correlation, and in gray, these dots are profiles which are core halo, as I showed before, but with halos with the tails of the halo following a power law similar to the one of simulation of given radius. So another important point is that, well, in diamond is the Milky Way here, but another important point is that the maximum mass for a particle mass of 50 keV, the critical mass of the central core, is 2.2 times 10 to 8 solar masses, interestingly. So this is the case that the degeneracy pressure, when becomes highly relativistic, can no longer support gravitationally the gravitational and become unstable while reaching this critical mass. This thing I'm showing here in words can be demonstrated theoretically and formally from this proportion here, from the turning point criterion in general relativity, but also from thermodynamics, showing the second variation of entropy until the system became unstable. So on both criterion coincide. This is very nice to show that this concept usually applied to neutron stars can be extended and generalized for system of fermions of finite temperature as this one, and lead to this critical mass. This is interesting value because this value may provide initial seed for formation of supermassive black hole in active galaxies, because you can imagine that when this halo, that the halos now are born of core halo nature at high redshift, and therefore you don't need to start with a population 3 star and then undergo hyper-enton accretion in short times to form the observed supermassive black hole, for example, at redshift 7 of 10 to 8, but you born with this, out of this theory, it is possible that the central core is already born at high redshift, and then if the conditions are given, it can collapse to a supermassive black hole directly, and then, of course, keep growing up to 10 to 9, 10 to 10 solar masses later on. So this is my last slide, showing that from our results, our results suggest that normal galaxies, so non-active galaxies with central object masses of 10 to 6 up to 10 to 7, may not be, which of course do not show generally jets nor activity, may not be supermassive black holes, so singularities, but dense cores of dark matter, and that's why you don't see activity. But for larger galaxies, or active galaxies, which masses of the central object are typically larger than 10 to 8, you do, which have jet emissions and hard X-ray, you do need a black hole at the center, but in our model, it may be produced by the collapse of dark matter. Okay, so I will move to the conclusions. And so accounting for the quantum nature of the dark matter in the relaxation of halos, let me emphasize that this is not possible actual cosmological and simulations we do for classical particles. So it's important to introduce the quantum nature of the particles.
Lasciato tutto il meeting.
Yes. So can lead to novel profiles, which are long-lived and develop a compact nucleus surrounded by a dilute halo. These core halo profiles can explain the galaxy rotation curves, but also provide alternative to central black holes in non-active galaxies, offering explanation, for example, to natural explanation for intermediate massive black holes in terms of these dense cores. Then, for particle masses of 50 keV, both the black hole and the core of dark matter can explain precise astrometric data of S2 clusters, of S-cluster stars, including S2. But besides the S-star cluster and the Milky Way rotation curve, altogether, this continuous core halo distribution can explain the post-pericenter passage of G2 without invoking a drop force. And interestingly, and finally, for the same particle mass used to explain our galaxy, the critical mass for gravitational collapse of these high-dense dark matter cores can lead to a supermassive black hole formation of masses of up to 10 to 8 solar mass. Okay, I stop here, and thanks a lot for your attention.
Okay, thanks, Carlos. So I have a very short question. Can you model explain the precision of S2 star?
Oh,
Bit of
very-
precision.
yes, this is a very good question. Indeed, indeed we can. Let me say a few words about that. Precession, relativistic precession of S2 star was up to now measured 2 years ago, or by the European team, showing that it is consistent with general relativity. So indeed showing a precession, which of course it wouldn't exist in Newtonian gravity. When the star was passing at the pericenter, at second pericenter passage. Interestingly, it was shown also recently by the American team that the precession of S2 happens at, or is more visible at apocenter. And it is very interesting that we are calculating right now this, the precession, and it may lead to some surprises because we have to wait to the second apocenter, well, third principal apocenter passage of S2 to see which model is preferred, if a black hole or a dark matter core, given that, as you can already imagine, the extended distribution will generate an extra precession effect due to the extended mass out of the orbit.
Okay, thanks.
But
So-
new results coming soon. New results coming soon.
Okay, we're looking forward to see.
Okay, good.
I think this is the end of the block 1. Because the chairperson of block 2 is not here, I continue to chair the next block. Yeah. So Raymond, should we have coffee break or we should continue?
Sorry, there are